Welcome, mathematicians. Let's prove triangle congruence by side, 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 and hypotenuse leg. So our essential questions: what can you conclude about two triangles when the corresponding sides are congruent? Or of two right triangles when you know the hypotenuse and a leg are congruent? All right, of our 5 different shortcuts to prove triangles congruent, so far we've learned about side, angle, side. Today we're going to do side, 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 and the hypotenuse leg. All right, so the first theorem is the side, side, side congruence theorem. If 3 sides of one triangle are congruent to 3 sides of a second triangle, then the two triangles are congruent. Our implied statement reads, side, side, side implies congruent triangles. So observe the markings of our example picture here. So if side AB is congruent to side DE, and BC is congruent to side EF, and AC is congruent to DF, then the two triangles are congruent. All right, so let's have our first proof of the lesson, example 1, using the side, side, side congruence theorem. Here we are given that side KL is congruent to side NL, so make sure you take time to mark your picture if it's not already marked. And then KM is congruent to NM, so we have a different number of markings for these two corresponding sides. And then we're trying to prove that these two triangles are congruent. So I already see that the triangles are sharing the same side. So that's always going to be somewhere in your proof when two shapes are sharing the same side. All right, start by including your givens at the beginning. And we have 2 givens. And we put the S's out to the side to indicate our parts. And we just need a third part since we're using the side, side, side congruence theorem. And we have that third part, as mentioned before. So put that in your proof as a statement, and the reason is the reflexive property of congruence. And put your third S out there to the side, and so we can see that we have the 3 parts that are necessary to now state that the two triangles are congruent. And our reason, justification, is that SSS implies congruent triangles. All right, so this parentheses with all these numbers. Let's take a moment to discuss this. Basically, you need to include these numbers that represent the statements that are needed for this final conclusion. We needed to state that side KL was congruent to NL, which is statement 1. We needed to say that KM was congruent to NM, so that's statement 2. We needed to say that LM is congruent to LM, which is statement 3. And because of all 3 of these statements, we can conclude these triangles congruent. So the reason is all this, and we're including the additional statements that are necessary. So this is an important part of a 2-column proof. We don't need this when we use the flowchart proof, because the flowchart proof, all of these boxes would have arrows pointing to the same box. So this is a little bit different than the flowchart proof. And then just remember the 2-column style has all statements on the left and reasons on the right, which are your implied statements. All right, so let's practice deciding whether the congruent statement is true, explaining our reasoning. So let's take a look at number 1 together, and then I'd like for you to try numbers 2 and 3 on your own. So pause the video and try them on your own. So on number 1, triangle DFG congruent to triangle HJK. First of all, do we have enough in our statement and picture to conclude that the two triangles are congruent? And the answer is yes. From the diagram markings, side DF is congruent to side HJ, side FG is congruent to side JK, and side DG is congruent to side HK. And that is all 3 parts corresponding congruent. So triangle DFG is congruent to triangle HJK by the side, side, side implies congruent triangles theorem. Now you try number 2 and 3 by yourself. Pause the video and try on your own. Okay, take a moment to read the 2 explanations for 2 and 3 compared to your answers and see how you did. All right, example 2 is solving a real-life problem. Let's take a look at this image where we've got 2 benches. Explain why the bench with the diagonal support is stable. Our diagonal support is the one here on the left. Here's our diagonal support. While the one without the support can collapse. So that's the bench here on the right. So take a moment to kind of ponder this and see what you think. So pause the video and maybe write down some ideas of why you think the bench with the diagonal support is more stable than the one without the diagonal. All right, so here's one possible explanation. The bench with the diagonal forms triangles with fixed side lengths. So by the side, side, side implies congruent triangles. These triangles cannot change shape. So the bench is stable. The bench without the diagonal support is not stable because there are many possible quadrilaterals with the given side lengths. Okay, so let's take a moment to look at these three examples and apply the same idea. So let's determine whether the figure is stable and explain our reasoning. So if I'm looking at number 4, is this an example of a figure that is stable? And the answer is no. There's no diagonal forming any triangle. Therefore, there are many options for the values of the side lengths. So now consider number 5. Number 5 is a figure that is stable. The diagonal support cuts the original quadrilateral into 2 adjacent triangles, therefore fixed side lengths. No way to change shape. So by the side, side, side implies congruent triangles. These triangles cannot change shape, so the figure is stable. Our final example, number 6, is also not stable. The diagonal forms a triangle and a quadrilateral. And the triangle would be stable, but the quadrilateral is not, because there are many possible quadrilaterals with the given side lengths. So in conclusion, if your figure is split such that there are triangles only, then you have stability. But if you split and have a combination of triangles and quadrilaterals or just quadrilaterals, then it will not be enough to be supportable. All right, students, we have another construction. So far, every lesson has had a construction, and I haven't seen anyone who's practiced them yet. So please take time to practice this one along with all the previous lessons' constructions, and just see how it goes following the 4 steps, and bring your questions to class tomorrow. What you're doing is copying this triangle that's given using these 4 steps. So give it a try. So far, we know that side angle side and side 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 are valid methods for proving that triangles are congruent. What about SSA? So side side angle. Well, here's a picture that looks like it's a counterexample, because we have a scalene, obtuse scalene triangle here with 2 congruent marks on the acute scalene triangle, and matching second side and a non-included angle. A non-included angle means it's not between the 2 sides. So because of these 2 examples, we for sure can conclude that side-side angle is not always a way to prove triangles congruent. So one way to remember that this one won't work is, how about you rearrange those letters? Dope! That spells a bad word. So just remember, this is a no cussing zone. So SSA, or in other words ASS, will not work to prove triangles congruent. Hee hee. All right, our next theorem, the hypotenuse-leg congruence theorem, only works for right triangles. So this one is a special theorem. If the hypotenuse and a leg of a right triangle are congruent to the hypotenuse and the leg of a second triangle, right triangle, then the 2 triangles are congruent. So our implied statement reads HL, and in parentheses put an R for a reminder that that angle there must be a right angle, and it implies congruent triangles. So here we have our corresponding marks, and it doesn't matter which leg it is, at least one of the legs of the corresponding legs of a right triangle are congruent. And then here's our statements. So if side AB is congruent to side DE, and side BC is congruent to side EF, and angle C equal to angle F, and equals to 90 degrees, then the triangle ABC is congruent to triangle DEF. All right, so let's look at a proof using the HL congruence theorem. So our proof, we're given that WY is congruent to XZ, WZ is perpendicular to ZY, XY is perpendicular to ZY. So take a moment to make some marks. And noticing that the two triangles are overlapping, so one of the strategies might be that you separate the two triangles and then do your marks. So if you redraw the triangles so that they are side by side with the corresponding parts in the same position and then mark the given information, that could be helpful. So if you're having trouble matching the vertices to the letters when you separate the overlapping triangles, leave the triangles in their original orientations. So you can either just slide them away from each other or completely change orientation. All right, let's get started with our proof. We always start by stating the givens. So we have given WY congruent to XZ, reason, given, and it is one of our parts that we need. So I'm putting an H because it is the hypotenuse part of our proof. And then our other given is necessary to have in the proof because of the perpendicular segments. Reason, given. So our immediate next conclusion that we need to state is that if we have perpendicular segments, then we have right angles. So that's your next statement. So we state that angle Z and angle Y are right angles. Reason? Because we had perpendicular lines in the previous statement. So if we have perpendicular lines, then this implies right angles. And then we can conclude that if we have right angles, then we have right triangles. So we can say that WYZ and WXZY are right triangles. Reason? Because triangles with one right angle implies right triangles. So then once we've established that this is a right triangle, which these have to be stated in our proof, we have to state that these are right triangles. Next, we need another part. So we can see in the original that both triangles are sharing the same side, and that same side happens to be a leg. So we can say by the reflexive property of congruence that ZY is congruent to YZ. It's congruent to itself. And we put an L out here because it's our second part that we need. So we have everything we need to say and conclude that triangle WYZ is congruent to triangle XZY. And our reason is the hypotenuse leg of a right triangle implies congruent triangles. And again, remember to include in parentheses all the statements that you needed to come up with this conclusion. All right, here we have a final example using the hypotenuse leg congruence theorem. Real world example, we have a television antenna that's perpendicular to the plane containing points B, C, D, and E. Notice here at the base of the antenna is the plane that contains B, C, D, and E. Each of the cables running from the top of the antenna to B, to C, and to D are the same length. And notice that in our picture, all these three segments have congruent marks. So we're trying to prove that each of these triangles that are formed by all these segments are congruent. So we're given that AE is perpendicular to EB, so we want to make a mark of a right angle. AE is perpendicular to EC, so we make a right angle mark. A is perpendicular to ED, make a mark. AB is congruent to AC, which is congruent to AD, and again, make marks. Trying to prove these three triangles congruent. All right, and this time I thought it would be advantageous for you to read through a paragraph proof. And this could be an easier form for you if you've had a hard time with the 2-column or the flowchart proof, because you're just writing sentences and stating things that you're observing from one statement to the next, and it kind of reads and flows maybe a little bit better for you. So try to construct a paragraph proof and read through this one to kind of get an idea of how it works and see if this is a better option for you. Whew, that's all, mathematicians, for tonight. Bring your notes and let's practice tomorrow in class.